Good afternoon guys, we are team 14 and our project is Deep Learning Enhanced VisualSLAM System on Embedded Robotics Hardware. SLAM system is a system that simultaneously localizes and deals with map around itself. It should run in also real time. So VisualSLAM is a variant of visual variant of the system. So it takes only the images and it builds the map, and also it tracks its location in the system. When it comes to VisualSLAM, we have some inherent problems. So as you can see here, so VisualSLAM tend to perform poorly in dynamic environments. When there are a lot of moving people, VisualSLAM systems performs poorly, and also low textured area, and also most of the time unseen environments that are not planned for, they perform poorly. And also VisualSLAM system, because it's taking visual feed, most of them, though they are highly computationally complex. So this is an attempt by us to implement the OpSLAM 3 SLAM system in our embedded device. Our solution for that problem is to deploy a deep learning based VisualSLAM system on an embedded hardware. So when it comes to deep learning also performs better in generalized scenarios. Actually, when we talk about hand-drafted algorithms perform better in the environment that the authors are hoped for. And when it goes out of the context, it will perform backward. We use the deep learning based feature extractor called SuperPoint as our feature extract, our main feature extract. We use an optional segmentation part to segment out moving areas in our image as well. We have switched the normal op feature extractor with the SuperPoint feature extractor, and when deploying the SuperPoint feature extractor, we had to follow specific steps to deploy the SuperPoint-based feature extractor in our FPGA. And we followed VisualSLAM toolchain. With VisualSLAM toolchain, what we are doing is we are compiling our learned model into VisualSLAM format. So it's called X model. So to do that, first we will be quantizing our model to from float 32 format to int 8 format. And after that, we have to compile our model to be created into the VisualSLAM DPU. We assume this kind of network. In this network, there are learned layers are deployed in the DPU, but there are also some non-learned layers that are not supported by the DPU. So we had to implement those layers in the CPU side. So when we actually time the feature extraction process, all of the feature extraction was happening in the DPU under 90 milliseconds, but the CPU processing took much more than that, and it was a bottleneck of our system. To mitigate that issue, we proposed a pipeline feature extraction mechanism. So this is a 3-stage pipeline. In the first stage, the pre-processing will happen. And in the second stage, with the DPU, actually in the first stage, pre-processing will happen. In the second stage, DPU inferencing, the DPU will be inferencing the learned features in there. And after in the third stage, post-processing will happen in a parallelized manner. We are using data parallelism to implement that. Actually accelerate that feature extraction in the CPU. So after that, we will be there's an inherent problem in that kind of pipeline manners. There will be sequencing problems. Some of the extracted results will come before the others. Because of that, we have put a resequencer module after the feature extraction also. So in here, then we come to the SLAM system side. When we come to the SLAM system side, regarding the SLAM system side, what we are doing is we plugged out the normal feature extractor, normal old feature extractor used in the SLAM system, and we plugged in the SuperPoint-based feature extractor. So our pipeline into this. So the SuperPoint pipeline can actually run up to 50 FPS, but to align with our SLAM system, we ran it with 20 FPS, and we actually gave the results to the tracking thread of the SLAM system. And when it comes to the SLAM system updates, we had to change the type of features extracted in the SLAM system. So we had to change the feature matches also. Previous feature matches were using O feature descriptors. O feature descriptors are based on binary descriptors. Binary descriptors means the unique key generated for each feature is in binary, and the matching should be done with having distance. For this, we are using L2 normalization to compare two features. And also another optional thing we integrated into our deep learning pipeline is the segmentation method. So if we have a good internet connection, what we can do is we can offload the pre-processed image to a offline remote server. Then it will process our image at real time, and it will give us a segmentation mask, segmenting out any moving or unreliable objects in the area. It's another thing that we done that we used to deploy our SLAM system in the device. So this device is resource constrained. We can't actually compile this type of heavy system to integrate into this kind of low power system. So we used a remote server to compile the SLAM software. So what we did is we made a copy of our system root, byte-to-byte copy of our system root on a remote server, and we using Q emulator, we translated the instructions, ARM instructions to x86 format instructions, and after that we could emulate the system in there, and we utilizing the native compilers, we could compile the software within that remote server, and we transferred our resulting binaries to our board. So these are some other alternatives we use. So we first considered with the thermal RGB sensor fusion for the SLAM system, and we tried with knowledge distillation to distill the model to have less complexity. And also we tried with X-Suite, SFD2 and HFNet, but due to the timing constraints and complexity of our project, we stick with the SuperPoint-based extractor. This is the next part. So these are the alternatives we considered when deploying the deep learning module, the DNN architecture in our FPGA. So Vitis AI is the part that we are using, and this ping HLS is are the viable options, but we stick with Vitis AI because of the DPU IP support it's been giving, and the others were actually, some were not as much performant as this, and others took much more time to develop. And these are some other SLAM systems we consider. Sherwin's, this actually has more accuracy than the current base framework we use, but the problem was that it was built for stereo visualization only, stereo images only. In our SLAM system, because of the hardware constraints, we stick with monocular vision. And these are some results we have taken at our computer lab. You can see this is a 2x version of the evaluation we have done in the UAV lab. These are the results we have taken in the night. So in the night, this system performs moderately, and it sometimes loses its track, but with the OpSAM-free's robust SLAM system, it relocalizes itself after some time. and these are the results we have taken when we ran our system with the Europe dataset. So we achieved RNSE for absolute pose error of 8 centimeters. Yes, thank you very much.